Greetings all. This video is about the normal distribution. A normal distribution emerges when numerous independent random occurrences contribute additively to an outcome. A good example of this is if you measured the height of all residents in the city of Memphis. Collectively, the frequencies of height at all levels will form a normal distribution. In statistics, a normal distribution has specific characteristics. A normal distribution is a type of probability distribution that is symmetric about the mean. It is also known as a Gaussian distribution or a bell curve. If a variable v is normally distributed, the values of the variable are depicted on the x-axis from low to high, while the y-axis shows the frequency or percentage of the cases for each value of the variable. Even though many variables approximate a normal distribution in the population, in practice, we usually use sample data. Strictly speaking, the normal distribution is a theoretical distribution on which statistics can develop ways to measure probability. The normal distribution is theoretical because it always has the following fundamental characteristics. First, a normal distribution is symmetric about the mean. Dividing by the mean, the upper half and the lower half are mirror images of each other. Second, a normal distribution is unimodal. Specifically, the mean, median, and mode are all at the same position. Finally, a normal distribution is asymptotic, meaning that the upper and lower tails can extend very far from the mean, but never touch the x-axis. In other words, extreme values are always possible, even though they may have a near-zero probability of occurring. With this description, it becomes clear that a normal distribution is a special type of frequency polygon. It's used to describe the distribution of quantitative variables, and the values along the x-axis represent a ratio scale. Also, the normal distribution is not just a distribution. It is a family of distributions sharing the above-mentioned characteristics. What differentiates one normal distribution from another is their mean and standard deviation values. Here, I provided the equation that expresses the normal distribution mathematically. You can see in this equation that a combination of the mean and standard deviation values determines a specific normal distribution. Remember when we talked about individual scores, there is a process called standardization, in which any variable can be transformed into a distribution with a mean of 0 and a standard deviation of 1. When a normal distribution is standardized, we get the standard normal distribution, also called the unit normal distribution, that has a mean of 0 and a standard deviation of 1. The normal distribution is important because it connects raw scores, z-scores, percentile ranks, and probability in a remarkable way. We can use the properties of the normal distribution to calculate the probability of an event or a score occurring by chance and to make easy conversions between z-scores, raw scores, and percentile ranks. We have mentioned that the raw scores are marked on the x-axis. When the values are standardized, the z-scores can be marked along with the raw scores. Z-scores not only tell where a raw score stands relative to others, but also make it easy to determine percentile ranks. Knowing that a normal curve is asymptotic, it covers all possibility of event outcomes. The total probability under the curve is 1, or 100%. Because the distribution is symmetric about the mean, 50% of occurrences are above the mean and 50% are below the mean. In addition, the mathematical nature of a normal distribution provides a precise percentage of scores between the mean and a given z-score. This relationship is summarized in the normal distribution table on page 259 of the textbook. For example, a z-score of 0.45 has a percentile rank of 67.36. Meaning that about 67.4% of the scores are at or below a z-score of 0.45 in the normal distribution. I found this value in the normal distribution table by first locating 0.04 under the z column and then finding 0.05 in the top row to the right of z. The intersection of the 0.4 row and the 0.05 column gives the number 0.673. Reversing this approach, you can find the z-score at a given percentile and convert it back to a raw score using the formula x equals mu plus z times sigma. For example, the 70th percentile rank is between 0.6985 and 0.7019. So the z-score is between 0.52 and 0.53. If we take the average of the two and use a z-score of 0.525 and assume a mean equals 100 and a standard deviation of 15, we can convert the z-score to a raw IQ score of 107.87. Similarly, in a normal distribution, the scores are connected with probability through the standard scores. To show how a normal distribution makes probability easier, let's agree that probability is a number that represents the likelihood of an event occurring. It can be expressed as a proportion or a percentage, and its value is always between 0 and 1. For example, in a set of scores 2, 2, 4, 7, 8, 9, 9, 9, 10, and 15, the probability of getting a 9 is 3 out of 10 equals 0.3, and the probability of getting a 10 is 1 out of 10 equals 0.1. The definition of a normal distribution gives us the ability to calculate exact probabilities of values occurring in the distribution of scores. For example, the probability of getting scores below z equals 0 is 0.50, and the probability of getting scores below z equals 1 is 0.84. Putting these two pieces of information together, we know that 0.34 or 34% of the population will have scores between the mean and 1 standard deviation above the mean. If we want to know the probability of falling between two raw scores, only one extra step is needed: convert the raw scores into z-scores. The three characteristics of a normal distribution makes it very useful for describing the distribution of variables that approximate normality. We admit that a distribution of scores collected from a sample is unlikely to be an exact normal distribution. But if we have reasons to believe that the population from which the sample was selected is normally distributed, then in inferential statistics, assumptions can be made about the population, and the normal distribution can be used to make inferences about the population from the sample statistics.